Hello and welcome to yet another video on my channel. Thanks for coming back. In this video, we are going to learn a few fundamentals about relations that can be defined on a non-empty set. Now, if the set is empty, it is a trivial case and it is not that interesting at all. So we consider the set to be a non-empty set. Now in this video, as we proceed to understand the fundamentals of relations defined on a set, we shall consider a toy example or a working example to take us forward in this journey. Let us hence consider the set here to be a set called capital A. Now, the set is a mathematical structure which contains elements. These elements can be objects, it could be the names of your friends, it could be the alphabet, the letters of the alphabet actually, right? Or it could be the alphabets of all the languages that you know, it could be numbers, it could be anything, it could be a combination, a collection of objects and numbers and alphabets and letters and so on. For our case here, for understanding the fundamentals of relations on a set that we are defining here, let us consider our set over here to be, let's say, the set containing 1, 2, and 3. It is a small set, but it has got interesting algebra along with it. Now, in order to define the relation, we must look into something that we call in mathematics as the Cartesian product. Now, the Cartesian product is defined as a set again, right? And the set contains its elements in form of something called ordered pairs, right? So an ordered pair would look like two elements. Let's name them as x and y, such that we are interested in what element comes in the beginning position and what element comes at the end position. Those of you who understand computer science and data structures, this can be thought of as a tuple, right? Or a tuple, Tuple. This is immutable and it is important to know which one comes first, which one comes second, right? Now, in order to define a Cartesian product, we collect all these ordered pairs as elements such that our x belongs to the set A and y belongs to set A. Well, I could have written x comma y belongs to A, but for beginners, even for veterans, it might have brought a little confusion. Hence, there is no harm in being more rigorous in the definition. And this particular set is represented by A cross A, right? So you can think of this set to be, let's say, the product of two sets. Now, if we suppose want to write down explicitly the elements of this set, it would look like 1 comma 1, 1 comma 2, 1 comma 3, where the leftmost element is 1. You could also write them 2 comma 1, 2 comma 2, and 2 comma 3, where the first element is 2. And further, you have got 3 comma 1, 3 comma 2, and 3 comma 3. where the first element is 3 in each of these cases. So there are these 9 elements in the Cartesian product, right? So if we try to understand what is the number of elements in this Cartesian product, we should be looking at, the cardinality of the set A raised to the power of 2. Well, if you consider a cardinality of set A to be equal to 5, then the cardinality of A cross A, the Cartesian product of the set A with itself, would be 5 square, that is 25, right? Well, in this case, it is 9. You can verify that yourself. Right. Now that we know what a Cartesian product is, a relation R, right? A relation R is defined as a subset of the Cartesian product of the Cartesian product A cross A. Now this subset of the Cartesian product R could be of many varieties. That means there are multiple possibilities in which we can write down a subset of the Cartesian product. And mind it, we are not specifying which subset of the Cartesian product is a relation, right? So in this case, there is no restriction on the subset selection. You can select any subset of the Cartesian product, and that would be a relation. Let us now try to find out again the number of relations that are possible, right? So you see that the number of elements in the Cartesian product is supposed to be the square of the number of elements in the set A. So the number of relations is the number of subsets of A cross A, right? And we know that the number of subsets of a particular set is equal to 2 raised to the power of the number of elements in the set that we are considering. So in our case, right, in our example, number of relations is equal to 2 raised to the power 9, and that would be 512. You see, the humongous number of relations that can be defined over the set that we have chosen, having just 3 elements. Since we have such an overwhelming number of relations, it is just to understand or view what are the types of relations that we can define. Now, the first type of relation that one could think about is a reflexive relation. Let us look into the definition of what a reflexive relation is. The definition states that for all the elements, the important keyword here is all. So for all elements X belongs to our given set, the ordered pair X comma X must be in R. Now, if there is at least one element y for which y comma y is not there in the relation R, then it is not reflexive. Let us take an example, right? So for a relation, in our example over here, you see 1 comma 1, 2 comma 2, 3 comma 3, all of them must belong to the relation. This is the reflexive property. Now, let us look at another property which is called the symmetric property. For understanding the symmetric property, we will not start from the set A. Instead, we will look for all the elements in the relation R. What I mean is that we will look for all, again, we're exhaustive here. We look for all the elements of the relation which are basically ordered pairs, right? X, Y, such that, again, this condition is important, X is not equal to Y. If we can find Y comma X belonging to R as well, we will say that our relation is symmetric. So in our example of the set A, if 1 comma 2 belongs to R, then 2 comma 1 must belong to R. If this does not happen, then we will say that the relation is not symmetric. Now, if a relation is not symmetric, we have tried to define, in our literature, another type of relation, which is called the anti-symmetric relation. Okay, again here we shall have to look at all the pairs x comma y, right? Exhaustive, belongs to R such that x is not equal to y, our y comma x must not belong to R. Which means that in our example, if let's say 3 comma 1 belongs to R, then 1 comma 3 must not belong to R, right? If we find an element 3 comma 2, let's say, in R, and 2 comma 3 is also there in R, then it is not anti-symmetric. An important point to be noted here, after understanding what a symmetric relation is and what an antisymmetric relation is that there can be relations, and I shall write this in caps. There can be relation, relation, let me put an S, that are not symmetric as well as not anti-symmetric. Right? So we have got two definitions of symmetric and not anti-symmetric. Symmetric means that if x comma y belongs to R, then y comma x will also belong to R. Whereas antisymmetric says that if x comma y belongs to R, then y comma x will not belong to R. But there can be relations in which for some x comma y comma x is there, and for some other p comma q comma p is not there, right? Okay. Now let's look at another type of relation, right? Another definition which says that, well, you see, by the way, this is called the transitivity property. And if x comma y belongs to R such that x is not equal to y, and if y comma z belongs to R such that y is not equal to z, then x comma y, x comma z will belong to R. An important point for you to note here is the following. You see the y over here, right? The x comma y, the y in x comma y, and the y in y comma z. These two must be equal. Let us take an example, right? In our relation, over here, let us say that we have got 1 comma 2 belongs to R and 2 comma 3 belongs to R. Then 1 comma 3 must belong to R. If 1 comma 3 is not there in R, in spite of 1 comma 2 and 2 comma 1, 2 comma 3 being in R, then we will say that the relation is not transitive. Right. Now, having said this, let us write down two definitions. Right? So, the first definition is that of an equivalence relation. So, an equivalence relation is a relation that satisfies the condition of reflexivity. It satisfies the conditions for symmetricity, and it satisfies the definition of transitivity. Whereas, if there is a relation which is reflexive, it is anti-symmetric, and it is transitive, then we say that the relation is having a partial order on the set. Now, some people love to use the word poset, P-O for partially ordered, and S-A-T from the word set for this definition, right? So, equivalence relation is reflexive and symmetric and transitive, whereas a partial order on a set implies that it is reflexive and anti-symmetric and transitive. Now, on our given set, let us discover a relation R1 that is going to be equivalence. So since it is reflexive, 1 comma 1, 2 comma 2 and 3 comma 3 belong to the relation. Now let's say that 1 comma 2 belongs to the relation. Then since it is symmetric, 2 comma 1 will also belong to the relation. And as you can see, if you take 1 comma 2 and 2 comma 1, okay, let us first close this bracket here. Since 1 comma 2 and 2 comma 1 belong to R, you can easily say that 1 comma 1 also belongs to the relation R. Now if you reverse the order and say that 2 comma 1 and 1 comma 2 belong to the relation, this would imply 2 comma 2 also belongs to the relation. And hence our R1 is going to be a symmetric. Oops, not a symmetric. Of course, it is a symmetric as well, but this is an example of an equivalence relation. Now, let us look at an example when the relation is a partial order. A partial order is reflexive. See, we are constructing relations here. We have written down 1, 1, 2, 2, 3, 3, which means that the relation is already reflexive. Let us consider the element 1 comma 2, right? So 1 comma 2 belongs to R2, but 2 comma 1, can you see 2 comma 1? No, it does not belong to R2. Hence, the relation is anti-symmetric. We just need one example. That's it. And of course, we cannot do any transitivity here because 1 comma 2 is the only element with x is not equal to y, right? So the question of transitivity being defined is not seen here. Hence, our relation over here is a partial order. So in this lecture, we have covered what is the definition of a relation. A relation is a subset of the Cartesian product. We have found out what is the cardinality of a relation. Well, that's the number of ordered pairs. But the number of relations is also obtained over here. In this lecture, we also identified the definition of the reflexive relation, of a symmetric relation, of an anti-symmetric relation, and a transitive relation. Hey, by the way, we also have discovered the fact that rediscovered, or maybe understood, or maybe we are trying to recall this fact again and again, saying that a relation may be symmetric or maybe it might be anti-symmetric. Also, there can be some relations which are neither symmetric nor anti-symmetric. Further, we identified the definition of what an equivalence relation is, basically reflexive and symmetric and transitive properties must hold. And there is also a partial order on the set, which is called poset, which means that the relation is reflexive, antisymmetric, and transitive. Hey, thanks for watching.